Yeah, so tonight, I was asked to explore the my book Computational Engineering, which I wrote with the institution, how I came to write it, and more importantly, an overview of what it contains. Now, to add to the David's introduction to me, I mean, I'm sure like many engineers, I started making models as a child, you know, Lego, Airfix, books. Then, as a teenager, discovered computers, and I'm sure some of you can recognize some of those. These were the first three computers I used, only two of which survived the experience. Yeah, civil engineering back at Surrey, and then worked at a variety of companies over the years. Um, um, some of which logos, well, there are a few modern logos, not so logos were around at the time. The CFE ones changed a bit over the last 20 years, but yes. So I started as a structural engineer with a specialism in computing, and then became in computing with a specialism in structural engineering. So the book, I mean, I wanted a book which would explain broad sweeps of computing for structural engineers. And what I was really looking for was the equivalent of J. Gordon's structures, or why things don't fall down. Something which explained what and why, and not just a list of formulas. Though I did add a few useful ones at the back. But unfortunately, that book didn't exist. So I realised it had to be me who needed to write it. And so it sort of encompasses about 35 years of experience in engineering and computing, mostly aimed at graduates, but this thing has been picked up by senior engineers wanting to deepen their knowledge, as well as those more senior who want to understand what it is the youngsters are going on about. So most engineering books, they're a bit like car manuals. That they'll tell you how the engine works. And the idea is then is once you know the mechanics, then you expect to take the keys and just drive off. Whereas computational engineering is more about like a driver's manual, explaining what you might need to know as a practicing engineer. So it covers how we use computers, why we use computers, design methodologies, parametrics, gets onto FE analysis. That's quite a large chunk. It's quite a large subject of us. Moves into a favourite of mine, optimization, and then ends with a look to the future, artificial intelligence, machine learning, digital fabrication, cloud, and quantum computing, plus some thoughts on the future role of engineers, and of course some appendices. So, introduction. Why do we use computers to do engineering? The reason is they are very, very good at doing maths, and they're far, far faster than we can ever be. And they are without error, well, if programmed correctly, and without tiring, though possibly overheating, and without getting bored of all the mind-numbing tasks, because despite names like artificial intelligence, they have no minds. They can do our drudge work, freeing us up to do the interesting, the creative, the imaginative, the interpreting, the communicating, and the human design. Now, one of my personal bugbears is the confusion over the dual meaning of the word design. One meaning, understanding and interpreting the client's briefs and needs, working with the architects and other consultants to determine the best approach, form, layout, and methodology to meet those needs. And the other one, calculating beam sizes and rebar quantities. Now, number one is creative. Number two is mechanical. I mean, still pretty darn crucial. The devil is in the detail, and we must never forget things like the Hyatt Regency Hotel. Now, in my chapter on design, I very much focus on the scheme rather than the detail. In my case, there are plenty of other books which will go into the detail. So how do we do design? Well, not on a blank sheet of paper like this, but yeah, we have requirements and constraints. They speak for themselves. Those options, now these, for me personally, are the interesting ones. I've noticed that almost every year, the iStructE chartership examiners, they'll complain that the candidates struggle to find two distinct solutions to exam problems. I mean, obviously we all know the two options are a brace steel frame and a concrete moment frame. Well, maybe not. Alternatively, a lot of the students I've taught know that the two options are always a truss or a portal frame, which is similar, I suppose. Now, in engineering, we sometimes talk about creativity, which is not enough in my opinion, but it is, I think, in the options that creativity is most often found. Now, it is said that if all you have is a hammer, all problems look like a nail. Now, certainly, when I was preparing for my chartership exam, I decided to create an exhaustive list of all the possible ways to cross a horizontal gap, and likewise to keep a load at height. And I never did actually finish that list. It was possibly an infinite list, or certainly a very large list. Yeah, there are no excuses for just two options. For me, creativity comes from knowing what the options are and then choosing the best options from those. Now, Hermann von Helmholtz and Henry Poincaré put it more succinctly: creativity comes from saturation. The idea you got to learn everything, especially about the subjects, but also everything else. As engineers, we should also be learning from natural structures such as skeletons and muscles, shells and trees. We can also learn from art, and maths and sciences, in fact, from everywhere. Then there's incubation, thinking about the problem, sleeping on it. This part can take time. Then there's illumination. Finally, an idea. I mean, Murray Gell-Mann got his Nobel-winning quantum breakthrough by making a mistake in a lecture. But without the saturation and incubation, he would have never realized that was the answer he was looking for. And then finally, of course, we have validation or verification. You have your scheme, approximate sizes, but now you need to do all the analysis and details to make sure that it will actually work, as well as, of course, exploring how to make it better. Now, the Design Council put it a slightly different way. See above about there being more than one way to do something. Now, and they use the design double diamonds. Note that the discovery and the development phases, the design broadens. This is when you explore what the options can be. Remember, don't close down your options too soon. Then it's in the define and delivery stages that you must refine and concentrate on what the problem is and what the solution is. Now, and even this doesn't take into account the cyclical nature of design. So let's dig in a little bit deeper on the development phase and the method called parametric design. I mean, we all know that layouts are driven by constraints and dimensions. Yeah, we know too well when the architect changes something, making the schema a little bit larger or smaller, and then we start all over again. But with parametric design, we can plan for change by encapsulating all those constraints and rules into a geometric computer model, a design led by parameters. Now, these might be mundane things like span of a decking slab, or complex like the offset from a curved spline surface. Speaking of which, parametric design started in the aeronautical industry, whereas the first parametric design in the building industry, as far as I'm aware, was Frank Gehry's Guggenheim Museum in Bilbao, in Spain, which opened way back in 1997. Now, parametric design back in the 90s was on supercomputers running software designed for making fighter jets. Today, it's a much simpler CAD program like Rhino, as you see here, running what I like to call a plate of spaghetti script, or Grasshopper, which then generates the geometry. Then with various sliders to control things, and then export to FE for analysis, CAD for detail and documentation, and so on. Which, of course, brings us to BIM. I mean, BIM, building information modeling used to be about neutral file formats, but we've moved on from there. Now it's all about digital workflows, information flowing automatically from one program to the next. Though of course the underlying principle of data reuse remains the same. Now, to the validation of your designs, of course, using finite element analysis. Now, this was used back in the 1950s, aircraft again, and in the 1960s on buildings. Now, as far as I know, the first structural engineering use was by Arup on the Sydney Opera House. But if you know of any other examples, I'll be very interested to know. Now, FE analysis books, I find a little bit frustrating. They tend to focus just on the maths of the methods, which is great if you want to write your own program, but the majority of engineers I know just want to use a commercial program. So my aim here was to teach how to make the best use of models. A little bit of maths thrown in because it can be interesting. It can be useful to have some understanding of the methods behind the analysis. Now, as an aside, I think in the universities, FE maths is more likely to be taught than modelling, because having done marking maths is a lot easier than marking modelling. Modelling is an art, and therefore there is no one right way of doing it. Rather, there are better ways and there are worse ways, and of course, occasionally completely wrong ways. So, what is it? What is a model? So, it's a simplification of reality. It's not the real thing. For example, this is not a beam. And the supports don't totally represent everything about the real connection, but they are close enough for engineering. Yeah, the model is a simplification of reality, not reality. Therefore, all models are wrong. This is important to remember. A model is not the complete representation of the structure. It is not possible to build a totally realistic model and test it with everything the real structure will experience over its service life. Now, the closest we might get is to build a real structure out of steel and concrete and so on, and then test it to destruction and then rebuild it and so on. But I mean, even this model won't be 100% accurate. It won't, because of tolerances will change. Steel and concrete sections will be slightly different. The framework won't be quite plumb in the same way. Wind, snow, and earthquakes will not be exactly the same. We don't know what will happen over the next 50 years and so on. It is not possible to do it perfectly, but the art of engineering is to get answers that are close enough. So consider the stool paradox, which you may have come across. If you sit essentially on a three-legged stool, then your weight will be carried approximately equally down each leg. The design load on each leg is therefore it's your weight divided by 3. But if you sit on a 4-legged stool, will the design load now be equally divided by 4? Well, no, because the stool will not be perfectly built, and the floor it sits on won't be perfectly flat, and then only 2 or 3 legs will actually be fully in contact. So effectively, your weight will actually be carried by 2 legs, meaning the design load is now your weight divided by 2, an increase of 50% thanks to the addition of an extra leg. Now, when we build analysis models, we tend to assume that the structure will be perfect. The floor is smooth, the stool is even, each leg is perfectly in contact with the floor, and reality is not so neat. But on the other hand, structures often work the way that we design them. If they have enough ductility. In the case of the stool, the connections may have a little bit of flexibility in them, as long as they're not being glued. And the top may warp a bit, and so on. So, what is the best way to model the stool? Now, without answering that, building structures often have similar problems. At university, we tend to study statically determinate structures, and so pin supports are fine. If the footing moves, yeah, it makes little difference to the structure. But if you have an indeterminate structure, such as this, a multi-span beam, a moment frame, a raft, a retaining wall built on soil, then suddenly the support stiffness becomes crucial. And as you can see there, as I discovered as a graduate, the bending moments go completely haywire if you use infinitely stiff supports in these situations. Now, moment redistribution, some of that does happen because of plasticity, but a lot will also happen because of the error in assuming that the supports are infinitely stiff. Model the ground or support with springs of an appropriate stiffness, and you'll see that sagging increases, hogging reduces. Usually, multi-span structures, things can get strange, but the redistribution moment here purely by putting spring supports in. Now, do we really know how stiff the beam will be? How stiff will the ground be? Well, this is only approximate. How confident can we be in the results? Take an example, a steel beam rolled in a factory to European tolerance standards. Its cross-sectional area can vary by up to 4%, and its bending stiffness up to round about 10%, depending on exactly on the beam size. This means that even with a factory-made steel beam, there is no point in calculating deflections beyond two significant figures. Concrete beam stiffnesses vary even more, from both the tolerances and effects of cracking as they carry a load and so on. Now, FEA models are analogues of the real structure. Now, 1D elements, these are great when the stress flows are essentially one-dimensional. One dimension, the length, is considerably more than the other two. Then we have two-dimensional elements, which are suitable when the stresses move in two directions. So thickness, usually, is considerably less than the other two dimensions. And then we have 3D elements. Well, I'm sure you can guess where they're used. Now, these analogies break down when the stress flow directions change and the connections between the beam slab and the column. For this reason, a simple overall model is great for informing you of the overall behavior of the structure, but you'll need a more detailed model of a part of the structure if you understand exactly what's going on in that location. But you would definitely not want to model the whole structure in the detail required for a connection. Appropriate modeling. So what does make a good model? Well, it needs to be as accurate as necessary. So do a sensitivity check, vary the stiffnesses, the dimensions, do a p-delta or non-linear analysis. Are the results still close enough? It's got to be as realistic as appropriate. Remember that increased realism is subject to diminishing returns. Stop when it's not worth continuing. It needs to be as simple as possible, but simplicity comes with experience. I mean, my first FE model took over 24 hours to run back on the University mainframe. Well, straight speaking, it took 24 hours before it crashed. Today, I would achieve the same results in a model with perhaps 1% of the number of elements and considerable less crashing. The model has to be useful and relevant. Does the model give you the answers that you need? For example, static and dynamic analyses often require different models. The essential question you need to ask yourself is, what is the question you are trying to answer? Then make sure that your model is set up to achieve that. Now, it would not be a book looking at FE if it doesn't have some explanation of the maths behind the methods, but then you essentially got five minutes to cover the methods. So on the subject which will normally take up entire textbooks. So I'm going to keep it quick and simple and useful. Now, here we have a simple structure, and we know that when we apply a force to a structure, its deformation, called U, is proportional to the external force, F, and inversely proportional to the stiffness, which we call K. Or stiffness times deflection equals force. Now, if you look at this bar element, it, for simplicity, only has axial stiffness, and you'll note that it has stiffness in the horizontal direction, or the x direction here, and nothing in the y direction. We apply a force in the vertical y direction, it will give no resistance whatsoever. Now, strictly speaking, an element will have forces applied to both ends, and that will cause both ends to move. And again, keeping it simple, looking at only the forces and displacements in line with the elements. Now, it can be useful to write all the equations in a matrix form. So we can then use matrix maths to find all the displacements and all the forces. Now we combine all the individual element stiffnesses, individual stiffness matrices together to form a global stiffness matrix. And again, for simplicity, I've shown each one separately, but they'll actually overlap wherever they have a shared node. And again, for simplicity, we can write this as Ku equals F. Now, we need to find the displacements, but you cannot divide by a matrix. Instead, we need to multiply both sides by the inverse of the stiffness matrix. And no, I'm not going to tell you how to do that here. And it's not important. And so once we have found the nodal displacements, we can then find the forces, and these include interfaces and reactions. And from the nodal displacements, we find the stresses and strains and so on. And that, ignoring a whole host of details, is simply how finite element analysis works. Now, in the book, I'll build on from there. So P-delta analysis includes the geometric stiffness matrix, which accounts for the way that tensions can increase stiffness, compressions can decrease it. Now, you'll note that there will be some forces where the element and the geometric stiffnesses cancel out, causing the P-delta analysis to fail. The P-delta analysis, we're actually looking for those failure loads which cause the collapse. And we'll then get the multiplier on the applied load, which caused the collapse, and the deflection is the buckling shape. And we find this using eigenvalue methods. And similarly, we can use eigenvalue methods to find the natural frequencies of the matrix, and we then combine them with the stiffness matrix. And of course, more advanced, we can combine both the stiffness matrix and the mass matrix to give you a P-delta buckling analysis, P-delta dynamic analysis, and also get into non-linear methods. But yeah, time is far too short to look at those now. Errors. Hartford Civic Centre, Slepner oil rig, CTV building Christchurch. These are just 3 structural collapses caused by bad FE analysis. The first 2 thankfully had no casualties, but 115 innocent people died in the 2011 Christchurch earthquake, all in that one building. And we possibly might add in the Florida University footbridge to this list. As I said earlier, all models are wrong, but some are useful. So how can you make sure that your models are useful? The finite element analysis stands for, FEA stands for finite element analysis, but also finite element approximation. So no digital computer can exactly represent real numbers. I mean, 3.14, it's approximately equal to pi, but may or may not be close enough depending on what you're calculating. And the maths of FE analysis is to find the solution of a whole bunch of simultaneous equations. Now, if we're only trying to find, let's say, the intersection of 2 lines using simultaneous equations, then the answer is definite. But as we add in more lines and more lines, the intersection gets more and more uncertain. Statistically indeterminate structures are even more uncertain. So how do we get the best results from a model? Well, validation. This is ensuring that the model is valid. Does it answer the right question and in the right way? Is it realistic? Does it include important checks and details like voids, stability? Is the modelling appropriate? I mean, the Harvard Civic Centre model was invalid because it ignores important details, such as the way inbuilt connections induced large amounts of torsion in the members, the members of which had virtually no torsion capacity. Their analysis approach was also invalid as they did not check for buckling, never mind torsional buckling, which was actually the cause of the collapse of the structure. They did not ask the right questions. And then verification. The CTV building analysis model was also invalid. They did not ask the right questions. The model was only giving them the center point story drift output, and the building had asymmetric stability systems, so torsional drift was very significant, and that led to the collapse. Okay, and then verification. Verification asks whether the model is giving the right answers, as in errors. And one of the best ways of verifying the model is to have a very good idea of what the right answers are, what they look like, whether deflection, the moment, or the shear. If the results do not match up with your expectations, well, it's usually one of three reasons. 1, your model is wrong. 2, your expectations are wrong. And 3, the software is wrong. Now, in commercial software, it's very rarely 3. The most likely cause is either you did not understand the structural behavior correctly, or you made an error in the model. Either way, it's time to dig in and find out where you went wrong. Hand calculations are also a great way to start, with an even simpler model and assumptions. Assume a truss as a beam, or a tall building as a cantilever. Then use beam theories to get approximate answers. Schleppner A oil rig sank because a one-line beam shear cap force check was never done. So, apart from approximations inherent in FE modeling, where do the errors come from? Errors in units. I mean, that's possibly the biggest cause of errors, at least the models that I've seen past my desk. Confusions between newtons and kilonewtons, meters and millimeters, whether in the materials, the sections, the model dimensions, the loads. I mean, you can very quickly find yourself out by a factor of 1,000 or even 1,000,000. Over-restraining your model will cause errors. I mean, I remember one model where the engineer put pinned restraints at the ends of all his beams rather than pinned releases, and then complained that the columns had zero load in them. Lack of restraints can also lead to unstable models. I mean, just because you do not have forces in a particular direction does not mean you do not need restraint in that direction. A zero stiffness will always stop the analysis, or should do, whether on the model as a whole or an unconnected element. Torsion is often forgotten, but it can be crucial. I mean, forgetting it was a dominant factor in both CTV and the Harvard Civic Centre collapses. Inappropriate meshing. I mean, this can reduce accuracy, but it can be especially crucial on buckling analysis models. Meshing was also an important factor on the Schleppner oil rig. As a tip, keep halving the mesh until you halve the mesh size until the results stabilize. Large deflections will need a non-linear analysis. And note also, if it's a non-linear analysis, you must not combine or multiply analysis results. You have to make sure that you analyze factor combinations to get the right results. And of course, there is whatever it is you've forgotten. Now, you've got your model working. It's working well. Now let's see how about making it work even better. Now, optimization, I know, favourite subject of mine, but I think it's something that almost all engineers are interested in, whether it's from finding the lightest beam to making a bridge span several kilometres over the sea, just carrying its self-weight. And now, at last, we have the drive towards zero carbon construction from both industry and clients. I mean, the construction industry contributes, well, I've seen various figures. I've seen 8% to 30% of the world's greenhouse gases. I mean, the main emissions used to come from the service life of the structures of the buildings, heating and cooling. But improved insulation efficiencies have greatly reduced those. Now it is the structure that is a major source of emissions, and we need to do our bit by building more efficiently. And I think optimization is one of the main tools for that. But I also hear many opinions as to what optimization actually is. Now, in its simplest term, it is just minimizing the cost of something in the design, subject to various constraints. Now, I'm not sure if the standard formula here is actually useful, but it seems to be a law that all text on optimization must include the formula. So here it is. But what does this mean? It means, put it another way, we are looking for the best solution amongst a set of feasible solutions. But it is up to you to decide what that range of feasible or possible solutions is. We need to computerize the optimization. To do that, we need a cost function, a way of measuring just how optimum or efficient a solution actually is. And you need to decide what variables you are going to explore to find that optimum. And as long as you know what is and what is not acceptable, for example, the structure cannot fail, and it also must not deflect too much. And if you decided you're going to minimize for cost or weight or construction time or environmental impact of the structure, how are you going to go about doing that? Now, there are three main categories of optimization. There's the section optimization, which is determining the best section size, which is perhaps the simplest option, but it also has the least effect on the overall cost of the structure. Then there is shape optimization. This looks at the shape of the building, the truss, or the section. And then there's topology optimization, which looks at the scheme as a whole. Span directions, numbers of columns, materials, and so on. Now, topology has the largest effect on the end result, so should actually be done first. As an example, in 2012, the incoming ISRT president, John Nolan, his inaugural address gave a simple and very powerful example of topology optimization on a simple single-story industrial building. This is a portal frame. But do we span the roofs in the short direction? And if so, is it best to have 2, 3, or 4 or more bays? If we span in the long direction, we have 4 up to 9 bays or so. Do we put columns everywhere, or do we use hit and miss layouts? Should we use moment bases to reduce the frame size, but which then require larger foundations? Even with this simple example, we're already dealing with over 100 layout options. Now, I've often wondered over the years, between things like trusses, what is the most efficient truss shape? Pratt's, Warren's, Fink's, Howe. I mean, what I didn't realise at the time was an Australian engineer called Mitchell found the answer about 100 years ago. Now, he used Maxwell's theorem of low paths, and Mitchell proved that it is possible to determine the most optimum truss, which, as you can see here, and these are now known as Mitchell trusses. Now, it is true they have quite a lot of connections, which connections can push up the costs, but you can also know exactly how close your truss is to the absolute optimum. And okay, if they haven't to date, they may be mostly known to tall building specialists and so on, but I would expect that these truss forms, these visual trusses, will be seen a lot more in future. Now, talk about topology and shape. Now, these can often be confused. Indeed, the boundaries between them can be fuzzy. So, here are 3 examples. Now, remember that the topology remains the same if you can stretch one form into another without breaking it. Hence, the quoted example of a donut and a coffee mug being topologically the same, and possibly also why they go so well together. Now, here the shape is a rectangle or a bowstring, while the topology is a number of internal elements in the truss. And shape optimization, I mean, this is getting the most from the structure by adjusting the location of the truss nodes, or the section corners, or the thicknesses, or the ridge heights, and so on, to get the most efficient answer. I-beams, for example, generally recognized as being very efficient, but even they come in a variety of shapes, depending on whether they're used for carrying bending, or compression, or composite action. And shape optimization is also essential if you're designing a compression only or a tension only structure, as the right shape should minimize the chance of buckling or wrinkles as is appropriate. And then finally, section optimization, which is something I think we're probably all familiar with, but can still throw up some surprising problems. Now, optimizing a section with a single statically determinate beam is pretty straightforward. But when stiffnesses interact, then it gets a lot more complex, even with this simple cruciform beam. 2 beams, same span, joined in the middle, central point loads. Even here, there are 3 principal optimum solutions. Now, actually, there are 4 more of these, but they're not quite so good. Now, if you're looking for at a more complex structure, which let's face it, most of them are, yeah, 2-way spanning variantals, truss, space frame, and so on. I mean, it can take a lot of iterations before you determine what the most efficient set of sections are. Now, I don't have time to cover everything concerning optimization here. I mean, I have been known to talk about it for several hours, and the book itself contains 2 whole chapters on the subject. As a teaser, here is a list of the principal heuristics or methods for optimizing a structure, or indeed for any other engineering problem. Now getting on to the state-of-the-art, cutting-edge artificial intelligence and machine learning. Now, the concept of artificial intelligence has been with us since the dawn of the computing age. I mean, the term itself was invented back in 1955 at the DART research project in the US, where a number of eminent mathematicians and scientists gathered to work out how to get a machine to simulate thought. Now, the expectation was if a carefully selected group of eminent scientists worked together for a summer, they should be able to make significant progress. Now, 70 years later, we know that they were rather optimistic, to say the least. But from their starting point, there have been many useful techniques and methods that have arisen, even if none of them have actually really come close to simulating thought. So, the initial quest for artificial thinking was done using things like symbolic logic or predicate calculus, and these completely failed to simulate thinking. But the natural language processing, for example, they were using did give us things like grammar checkers for our word processors. And another technique, natural language processing, is now found in most homes and pockets. So a machine learning system will pass speech sounds into words. Natural language processing groups the words into sentences, works out which parts are nouns, verbs and adjectives, instructions or questions. You'll then try to find the answer for you from the internet, or play the music of choice, or do something completely random. Also, search routines are artificial intelligence. Now, it is not possible to directly solve the question, what is the shortest route between 2 points? Well, apart from a straight line. Instead, AI research produce algorithms such as A* to intelligently search for the shortest route through a mixture of estimates, calculation, and data storage. Likewise, searching through unsorted databases is also an AI application, the most famous of which has become a verb, to Google. Now, another of the aims of AI was to encapsulate knowledge and to enable automatic decision making. Now, this could be in the form of a state search. Now, state search builds a tree of possible decisions and then navigates it to find the best answer, or at least the most promising route to the answer. And these certainly have proved successful in games like chess, as we see here. Now, games, of course, are formal. They have definite rules and they are bounded. Reality is not always so neat. And then we have neural networks. These have been around since the 1960s, initially very unsuccessful. Now, with faster processors, powerful training algorithms, and a huge amount of data supplied by the internet, they are now the dominant machine learning methods. Now, these are inspired by how neurons in the brain connect together, collating data and enabling pattern recognition. Now, artificial neural networks, they work by taking numerical data through a number of inputs, multiplying and adding them together in multiple times so the output indicates what is the right answer. Now, when they've been trained, if the answer is correct, then the links which gave this answer strengthens. If their answer is wrong, then the links are weakened. And the neural network is thus trained over thousands of iterations until it consistently, or at least generally, gives the right answers. Now, while machine learning methods such as deep learning have proved quite successful at applications like, videos of kittens on YouTube, in structural engineering, we have the problem of a lack of suitable data to train the systems. Now, hopefully this will change in future. And we will see more AI and machine learning engineering assistants in the future helping us with our tasks. Though I do not see them taking over, thinking about the most dull options. Now, computing has made huge changes in my lifetime so far, and I foresee even more coming. AI and machine learning will increase their presence, but I think the major change will be due to climate change and our efforts to mitigate that. So, yeah, the main thing we must do is work out how to build using less material. We must use less. We must also build less and refurbish more. Only doing the new builds when that is not an option. And optimization is going to be a significant tool for us in future, whether automatically exploring the structural topology, shape, or sections. And I know that there is a fear that optimization could reduce factors of safety, but I think you'll see that improving the topology and the shape of the structures will improve efficiency without compromising safety. And certain safety and robustness must always be there. There's also the concern that it could increase cost. Now, in some circumstances, this might be true, but by no means. I mean, more efficient construction should be cheaper. There's also an increasing number of clients who want to ensure that their projects are environmentally sound. Now, on the plus side, reducing the cost of structures will mean more effort, so it should mean more fees. And then there are other technological advances that we don't have time to discuss now. Mobile computing, it's there already, but that will increase its impacts. And I think many structural engineering teams will have struggled far more over the last 2 years without laptops and mobile phones to keep their businesses going. And of course, enabling me to talk wherever you are in Yorkshire or indeed the world. Cloud computing. This will reduce the need for local high-spec hardwares, enabling more mobile applications. And then there's quantum computing, which promises so much, but at the moment we don't know yet whether it will deliver or not. Now, and unfortunately, it's far too weird to explore now at the end of this talk. Maybe another time, but it certainly does get a whole section in the final chapter. So, as I mentioned, all these topics and more are covered in computational engineering, and I'm very grateful it's been very well received and attracted some amazing reviews from around the world. I'll also point out that there is a sale on the iStructE website. So the more books you buy, the bigger the discount you get. For example, Computational Engineering makes a very good pairing with Conceptual Design of Buildings, which has also been written by members of the Yorkshire Regional Group. And so on that point, I will say thank you very much. And are there any questions?